Hello, this is Mr. Pruitt, and today I'm talking about velocity versus time graphs. This is the second part in our series about kinematic graphs. So, looking back in review, there's really four important parts of these kinematic line graphs, and the big things are the points that make up the graph, each individual point that makes up the graph, the slope of its line segments, the quadrant that it's in, and then what we call the area under or over the curve, which is basically the area between the graph line and the x-axis. Today we're looking at velocity versus time graphs, and so when we look at it, we're going to see that velocity is on the y-axis as the dependent variable, and time is on the x-axis as the independent variable. The velocity versus time graph plots object speed or velocity over some period of elapsed time. In this example, you can see that the curve, which is just a big fancy name for the line that makes up the graph, is made up of multiple points. It shows both positive slope and negative slope, and that it occupies quadrant 1 and quadrant 4. Now, each point on our velocity versus time graph represents the instantaneous speed. So at this point, or at one of these points in between, maybe right here, that is how fast that object is going right at that instant. Okay, that's why it's the instantaneous speed. Now, if this object were a person that was running a race, each point would represent that person's speed at a specific time during the race. Now, as we move through the race, you'll notice that the person is actually moving at different speeds at different times. But we can look at the speed in two different ways. There is the instantaneous speed, which is what it is right at that instant, or then there's the average speed, which we can find by looking at the slope here. Now, anytime that the line crosses the x-axis, that it's on the x-axis, the object at that point is at rest, because when we're thinking about velocity being on the y, whenever y is equal to 0, then the object that we're looking at, or whatever the runner we're looking at, or whatever, would have to have been stopped at that point. All right, so let's look at the shapes real quick. As we go through this, we're just going to look at it by different topics. So if we were to look at the shape of a velocity versus time graph, basically they come in three shapes. We can get a nice flat horizontal line. We could get something that's linear and has a non-zero slope. So a line that's basically going either up and to the right or down and to the left. And then we could look at it as we might see a curve. So let's figure out what these means. If the line segment is flat, like in this graph, the object is moving at constant speed. Just means that there is no acceleration. It's going the same speed all the time. If the line segment has this linear non-zero slope in the velocity versus time graph, then the object is showing constant acceleration. And what that means is that it's accelerating, its speed is changing, but it's changing at the same rate over time. So the rate that the speed is changing between seconds 2 and 4 is the same as the rate that it's changing between seconds 4 and 8. Now, if we have this curved line, if we see something curved like this, uh, the object's acceleration at this point is changing. It just means that at this point it's accelerating faster at the beginning than it is over time. And if you think about this, this might be a pretty real life example of what happens whenever you take off in your car from a stoplight. You initially get up to a speed very quickly, maybe 40 or 45 miles per hour, and then your acceleration starts to slow down as you go to higher speeds. And this would be kind of representative of what you're seeing there. All right, so on your paper, you should see a graph like the one that you see to the right here, a velocity versus time graph. What I want you to do is just pause the video for a moment and circle and label the areas of the graph that show constant speed, that show constant acceleration, and that show changing acceleration. All right, so if we want to try to figure out the direction that the object's moving from the velocity versus time graph, we look at it a little bit different than we did in our previous graph. The direction of the object's motion is just determined by the quadrant that the line or the curve is in. Okay, so if the curve is in quadrant 1, like it is up here, then the object is moving in the positive direction. Or if the curve is in quadrant 4, like it is in this lower part, then the object is moving in the negative direction. So in this case, what we might see is that we had some kind of an object that was moving to the right. If right is the positive direction, they're moving to the right, and then they came to a stop, and now then they turned around and they're moving back to the left. All right, so slope of the velocity versus time graph indicates the acceleration of the object. Okay, so if we're looking for the average, that constant acceleration, or the average acceleration over time, then we would be looking at the slope. Positive slope, like this, indicates that the object is speeding up, and negative slopes, like this, indicate that the object is slowing down. So in this case, what happened was that our object sped up to about 8 meters per second. It remained at constant speed at 8 meters per second for 5 seconds, and then it slowed down over the next 5 seconds until it stopped. Then we have positive slope in we have negative slope in quadrant 4, but what's happening here is that it's turned around, and now it's speeding up in the negative direction. And then as it again, maybe there's a stoplight or something, it begins to slow down, also in the negative direction. But now we're moving. If we were moving to the right up here in quadrant 1, now we have sped up to the left and started to slow down again. If we were to calculate the object's acceleration between 15 and 20 seconds, we would come up with negative 1.6, using the same calculation that we used on the position versus time graph, that the slope is equal to y2 minus y1 over x2 minus x1. So plugging in coordinates for these points 20, 0, and 15, 8, we come up with negative 1.6 as the slope. And that would be its average rate of acceleration in the negative direction. All right, so the last thing that we look at, sometimes we look at what we call the area under or over the graph. And what that is it's the total area between the curve, between the lines, and the x-axis. So it would be this area right here, and it would also be this area right here. Okay. Now, what that does is it tells us the total distance it's traveled by the object during that period of time. So, from the velocity versus time graph, it's probably the most versatile of the three kinematic graphs, because we can figure out distance traveled or position, we can figure out speed, we can figure out acceleration, we can figure out direction. Uh, so we can pretty much find all of our kinematic quantities, all of those things that we use to describe motion, from this one graph. This one is probably the most useful one. Now, if we wanted to find the area under the curve, let's say that we wanted to know how far this object had traveled between 0 and 10 seconds. The first thing that we would do is that we would let me get a different pen. Is that we would draw a line down from wherever we want to know on the curve, down here, and we would kind of section off the area. So if we wanted to know from 0 to 10 seconds, we would draw a line down here, and you'll notice that we've got this nice red right triangle right here. I'm doing a really lousy job of filling it in. But you can see this right triangle right here. Now we need to find the area of this right triangle, and that will tell us how far we travel. So the formula for area is 1/2 base times height. That would be 1/2 of the base, which was 10 meters or 10 seconds, times the height, which was 8 meters per second. So 1/2 of 10 is 5, and 5 times 8 is 40. So this particular object has traveled 40 meters uh, in the first 10 seconds of its trip. All right, I'm hoping that this explains everything that you need to know about this particular type of graph. We will be doing something with this on Tuesday during